In this video, we're going to be going over a molar flux problem where we have dry nitrogen flowing through a pool of water and slowly evaporating it. And we're going to explain the net molar fluxes for both the nitrogen in the water and explain driving forces to kind of show why any of this is even happening to begin with. So I've already kind of drawn out the system here. We have this tube with a little, I'm going to circle as I do this, a little bit of water throughout here. We have nitrogen up above that is flowing throughout at 1 bar, and we have this sort of nitrogen water kind of mixture up above. So why does this evaporate the water? Well, this has to do something with molar fluxes and how molecules interact with each other when driving forces are introduced. So when we talk about molar flux, immediately what comes to mind is some concentration gradient, because if we observe the concentration gradient across some graph where we have position and concentration, we can kind of derive some, we can derive at least some value, or not some value, we can derive some behavior of the net molar flux. So what I'm going to do is I'm going to go ahead and I'm going to go ahead and graph a rough sketch of what water and nitrogen would be throughout the system, with some concentration and distance, which I'll call 0, but this is 1 meter. And we'll kind of use some math and we'll use some common sense to kind of begin this problem. So when we do this for water, let's go ahead and consider what concentration is. Concentration is moles per volume, right? How many molecules you have in a space of some dimension, right? So if we take an expression for the ideal gas law, which is PV equals nRT, for the system, concentration would just be pressure over gas law times temperature. That would be our concentration equation, right? So what we can do is, if we want to find what our concentration is at this distance of 0, where we have this kind of saturation line, so P, so we have our saturated pressure, what we can do is at least have a starting point for this concentration. So how can we find the saturated pressure? Well, what we can do is we still have some starting equations. We know that the temperature is at 323 Kelvin, and we know the pressure is at 1 bar, which is equivalent to 1001, 325 Pascal, right? What we can do is you could use Anton's equation, but I'm going to use the Clausius-Capron equation in this case. I hope I'm spelling this right. Use the Clausius-Capron equation, which is the natural log of the pressure of the partial pressure that you want over an observed pressure, which is then equal to your delta enthalpy of vaporization over your gas constant R, and then it is 1 over the temperature, or 1 over the second temperature over 1 over the first temperature you're observing. So I am going to, in advance looked up the values for the delta H vaporization so that we could just quickly derive an expression for pressure, because really this is just showing how we're getting the partial pressure at this case, which I know the partial pressure here, which is P saturated of H2O. This should equal something like 1.21 x 10 to the power of 5. Should be about something like that. So we're going to go ahead and proceed. Now that we know this value, what we can say for the concentration is that it equals 1.21 x 10 to the power of 5 Pascal over a point, which will leave us as R, multiplied by temperature. Give me 1 second. I'm going to go and calculate this. I'm actually going to hold off for a little bit. We don't really need to use this equation right now because we're not concerned about the We're not concerned about the actual concentration number right now, but we do know that there is some positive value of concentration with this because we're just going to do a rough sketch of what's roughly happening with concentration. This will become more relevant as we solve for the uh, partial pressure of nitrogen to see what its concentration could be. So we know that it's some positive value, and we know that if we're starting at 0 meters here, we know that as it begins to travel up and away from that source of water, that its concentration is probably going to get lower until eventually it reaches this top membrane over here to a very like infinitesimally small number until basically it's zero. And it's probably not a straight line, but again, this is just kind of to show general trend. We know that we have a net molar flux here because we have so I'm going to pretty this up a little bit. This is change of distance, and this is your concentration. We know that our concentration is going to go down and eventually basically equal zero once we reach this 1 meter mark, because at that membrane, it diffuses so much to a point where basically it has nowhere, there's nothing else left to diffuse. So let's go ahead and observe nitrogen when we do this. Nitrogen is starting from a source from up here, from some vent or something. And it's starting at 1 bar and it goes into our system here. So we know that its highest concentration is likely going to be at this 1 meter mark. So as it's traveling down, it's probably going down as well. However, something to note is that it's not going to completely kill its concentration. There's still going to be some concentration, but rather than water, which was able to kind of just diffuse until eventually it was done diffusing and had nothing else to diffuse, nitrogen, you can imagine it just kind of hits this wall. If you imagine nitrogen flowing in, it's just going to hit this water and just kind of sit on top of its boundary layer. Well, why is that? Why is it not proceeding forward? An analogy our professor said was, imagine it almost like a fish swimming upstream. Yes, it has a driving force moving up, but the water has a driving force moving down. And so it doesn't want it to exist. I mean, it doesn't have a net molar flux because it's just working against another driving force. So effectively, its net molar force is zero. And it has a concentration at this point. It's just sitting on top of the water boundary layer in this case. So we know that it's going to equal zero here. So how can we express that? How can we kind of mathematically represent that? Well, let's go ahead and incorporate something called Fick's law. And go ahead, kind of section this off, because now we're kind of getting into like actual calculation territory. We're going to be looking at Fick's law. Now, Fick's law is a way for us to find the molar flux of an individual component. And then it allows us to kind of, in the same way that we've done heat diffusivity and net diffusivity, we're going to do this for net molar flux as well. So we have Fick's law, which equals some molar, uh, some molar flux, which is equal to the negative concentration of your species multiplied by its diffusivity multiplied by some molar fraction over some distance, right? Or change of molar fraction, sorry, over some change of distance. So if you wanted to make the net equation in this case, let's do it for nitrogen, right? We have the molar flux of nitrogen, or the net molar flux of nitrogen equals this this molar flux of nitrogen. And then this is going to be plus the molar fraction, or sorry, let's go and make this Y because it's a gas molar fraction, plus the molar fraction of nitrogen of the total molar flux. So if we, luckily what's nice is that the total molar flux is a very simple equation. It's just the net molar flux of its system, to which this is a two-component system, so we have only water and nitrogen. So our total net molar is NH2O plus N2, 2O plus N2. Okay. So how can we think of this expression? Well, we said that because it doesn't push through this water and instead just kind of sits on top of it, that there is no net molar flux. So if we take the net molar fluxes of nitrogen and set them equal to zero, what we have is the molar flux of nitrogen equals the negative of the molar fraction of nitrogen. Sorry, should probably make this one, two, equals the net molar flux of H2O, which is actually kind of a beautiful equation because this kind of is saying what we were saying, that water has a driving force moving upward and it's canceling out the downward force of the nitrogen. It's at this kind of boundary layer. So this equation is, in my opinion, pretty awesome because it shows what we were trying to solve for. That's all well and dandy, but I want to solve for, let's say, I want to solve for some concentration at any point of this. I want to be able to say, or actually, wait, no. Sorry, my bad. My bad. I said the wrong thing. So, oh, sorry, hold on. Let me take care. I'm having some tech issues right now. I'm sorry for the abrupt. My iPad crashed and stopped recording without my knowledge, and so I'm gonna have to do this part again. So sorry for the abrupt cut. So we have to go ahead and find the net molar flux at water at this point. So we proved that for nitrogen, it would equal zero at this point because remember, it reaches that boundary layer, it can't push through. So we're going to say that the net molar flux of water, this equals the molar flux of the water plus the molar fraction of the net molar, which is net molar of H2O plus net molar of nitrogen. So we said that this equals zero from our previous evidence. And we know that for this concentration, it's going to equal, let's say for J, this is negative concentration diffusivity times the change of the molar fraction of H2O over change of distance. And then before I even continue from this point, I'm going to actually set in the values for concentration here. This is going to be pressure of H2, or no, this will be pressure of our system multiplied by diffusivity. And this is going to be multiplied by our gas constant, multiplied by our temperature. And then this will be plus the molar fraction of H2O times the net molar flux of H2O equals H2O. Okay. Oh, wait. Forgot one crucial part. This is multiplied by the gradient, which is 2O, and then this is over d of z. Okay, so now what we're going to do is the way that we would solve this is that we have separable equations, specifically d of z and d of mole fraction, and we're going to go ahead and separate them and integrate is what we're going to do. Just make sure we're recording. Okay, sorry, I'm getting paranoid about that now. So if we separate them, we get something like net molar fraction of H2O. We're going to move this over to the left side, and when we do that, we get 1 minus molar fraction of H2O. And then we can divide the left side by this. So just to kind of keep track, we have 1 over molar fraction of H2O. And then we can also multiply both sides by d of z to get rid of it on this side and move it over there. So we should have an equation that looks like mole fraction of, I'm going to put this meter, net mole flux of H2O multiplied by the change of distance equals negative pressure, diffusivity, gas constant, temperature multiplied by So it'd be 1 over 1 minus mole fraction of H2O multiplied by the change of mole fraction of H2O. So now we have our separable equations. What we're going to do is integrate. Mole fraction H2O is just a coefficient. Same thing for the concentration and diffusivity on this side. When we do this, we're going to get the change of distance here is just from the beginning of the tube to the end of the tube, so it should just be 1 meter, right? Makes sense. This is mole fraction of H2O multiplied by 1 meter, which I know it's multiplied by 1, but the units of m are going to be important when we have the final number, so it's important to keep the 1 meter there. And then for this guy, anything uh, that is 1 over the factor that you're integrating is just going to turn into natural log. So this is going to be natural log of, oh, I completely forgot. This is going to be, we need to do our molar fraction here. So the molar fraction at the beginning is pretty convenient because all we can do is just say we have our P saturated, which we solved for, and then we have our P total. So our P saturated in this case was 1.21 x 10 to the power of -4 over 10, and our total pressure is 101.325 Pascal. So what's nice about this is that if we just simply find the fraction between them, we'll know what the actual concentration is of our system just due to the rules of partial pressures. So if we do this, this should equal, I did the calculation in advance. It should be something like 1 point, no, sorry, 0.199, something like that. So if we do this, we have our starting mole fraction is 0.199, and then we end it at 0, because remember we said that once it reaches this point at 1 meter, it's essentially dissipated until it's nothing, right? So we have natural log of this would be 1 minus mole fraction of H2O integrated at these values, which means that we should have something like natural log of 1 over this would be 0, the 1 minus that this would be 0.879, right? Am I crazy? I think that's right. And then we're going to multiply this by our units over here. So I wrote in advance the gas constant in Pascal conversion so that we can make this easy for us. The pressure at this case is 101.325 multiplied by the units here are going to be kilograms per meter second squared. Second squared. Diffusivity is going to be 10. What did we say it was? 10 to the power of -5, and then the units are going to be meter squared a second. Go ahead and shed this natural log away from us. And then this is going to be over the gas constant that I had put in for cancellation, which is going to be 8.314. This is kilograms, meters cubed, second squared, multiplied by mole, multiplied by Kelvin. And then this is going to be multiplied by the temperature, which is 323 Kelvin. Okay, so, and then we can divide everything by 1 meter. So I'm going to go ahead and cancel out some units really quick. We have no kilograms in our system. We divide by that. Makes this to 4. Let's see here. Actually divides that, so it's over 1 meter. Now it's meters squared and become meters cubed. Right. Let me go ahead. I'm going to go ahead and do calculations really quick and just make sure that these numbers check out very quick. All right, I just wanted to make sure my math was right, and it should be. So kilograms cancel out. These meters should cancel out until we're divided by, this would be, that turns into meters squared because of this guy. So we're over, change that, meters squared. We're over some moles, and then we should be over 1 second because these two should cancel out. We're left with 1 second. The kelvins cancel out, the mole goes on top. So this would be meters second. And then the actual numbers in this case, I just calculated, should be 4.86 times 10 to the negative fifth, which equals our molar flux of water. So this is our net molar flux for our system. And we derive this by first saying that using Fick's law, that the net molar flux of nitrogen would equal zero. And with that assumption, we were able to proceed forward and have only the net flux of water, the change of distance, or basically having it so our net molar flux of water was our only unknown. And then using separable equations to then integrate and then find that value based on the system and assumptions that we had set up.